function f is analytic in this region R, which contains two arcs C1 and C2. The arcs C1 and C2 intersect at Z0. Furthermore, the derivative of the function at Z0 is not 0. The image of C1 under f is C1 dash, the image of C2 is C2 dash. In the last video, we stated that the angle between the arcs is preserved under f. In this video, we will prove that. We take a point Z1 on arc C1 that is a distance r to Z0. Z0 is the intersection of the two arcs. Then we take a point Z2, which is also a distance r from Z0. Z2 is on C2. Next, we consider the complex number Z1 minus Z0. Now we have an analogy with vectors here. If we think of Z0 and Z1 as vectors, then Z1 minus Z0 will be the vector whose tail is at Z0 and whose head is at Z1. We could move this vector parallel to itself so that its tail is at the origin. Then this point here would be the complex number Z1 minus Z0. And any complex number can be written in this form. This is Euler's form. R is the magnitude of the complex number. Theta is the angle measured anti-clockwise from the positive real axis to the complex number. Well, actually it's theta 1. We're saying that the angle or the argument of Z1 minus Z0 is theta 1. Similarly, we can consider this vector here whose tail is at Z0 and whose head is at Z2. We can think of it as the complex number Z2 minus Z0. Its modulus is R, but the angle is different, of course. If we wanted to see this angle, we could move this complex number so this tail is at the origin. And then we'd measure anti-clockwise from the positive real axis, and that would be theta 2. Now we will be interested in the angle between these two vectors, or these two chords. That's got by the difference of these two angles, theta 2 minus theta 1. To see that difference, we just divide. Let's say take this complex number here, Z1 minus Z0, and divide it by Z2 minus Z0. So we divide this by this, the r's cancel, and we subtract the angles. So we get this complex number here, whose argument is theta 2 minus theta 1. So the argument of Z1 minus Z0 divided by Z2 minus Z0 is theta 2 minus theta 1. That's the angle between the chords. This angle here. It's not what we want, not quite what we want. It's close to what we want if we make r small. The smaller we make r, the closer it is to the angle between the two curves at Z0. That is the angle between the tangents to the curves at Z0. Now, the actual angle that we're looking for we call alpha. So we just take the limit as r goes to 0 of this quantity to get the angle between the curves. Now let's consider the image of the points Z0, Z1 and Z2. So they're in the W plane, of course. The image of Z0 is W0 as we've seen. The image of Z1 is W1. The image of Z2 is W2. Of course, the distances of W2 and W1 to W0 don't have to be equal to R. We will consider two chords formed by joining W2 and W1 to W0, and the angle between the two chords is beta. So like before, we will consider this vector here, or complex number if you like. It's W2 minus W0, and this vector, our complex number W1 minus W0. So like before, we will calculate this quantity here, but apply to the W's, and that'll give us angle beta. So this is what we have. I've replaced W2 with f of Z2 and W0 with f of Z0, W1 with f of Z1. Now we can rewrite it like this. I just plugged Z2 minus Z0 in underneath fz2 minus fz0, and you have to multiply it by it over here, of course, to compensate. Similarly down here, Z1 minus Z0 appears. Now, as before, we know how to calculate the angle between the curves. We just take the limit as r goes to 0 of this quantity. As r goes to 0, z1 and z2 are getting closer and closer to z0, which means in turn, of course, that w1 and w2 are getting closer and closer to w0. So these two chords are becoming tangents. In the limit, the two chords are approaching the tangents to the two curves at w0, and we want the angle between the tangents. So notice this quantity up here. Now this is just the definition of the derivative of f with respect to z at z0. So we're calculating the function at z2 and z0. We're calculating f, we're getting the difference in the function between those values, and we're dividing that by the difference in the value z2 minus z0. So we're approaching a limit as r goes to 0. So that gives us the definition of the derivative of the function at z0. And we know that for an analytic function, that derivative is independent of the way in which we take the limit. So the quantity underneath must give us the same result. So if we work out f at z1, f at z0, take the difference, divide the difference by z1 minus z0 and take the limit as r goes to 0, we'll also have the derivative of f with respect to z at z0. What about this quantity here? Well, we've already seen that. We had that up here. So in the limit, all of this thing here is approaching 1. The derivatives are the same. So ultimately we're taking the limit as r tends to 0 of the argument of this quantity over here, which we know is alpha, the angle between arcs C1 and C2. So the angle between arcs C1 and C2, which is equal to the angle between arcs C1 prime and C2. Of course, we can write this derivative as f prime at z0. So now you see that we need to impose the condition that this derivative is not 0. Otherwise, this quantity here will be 0 over 0. And as we know, 0 over 0 can be anything we like. It's undefined.